you never change.
I don't. Oh,
Just look the same as out there's fine. Okay, good.
Hello.
where did this link come from? I posted it. I don't know what I'm doing with these links. It's because I don't even know this link is requiring me to admit people, which I hate.
Well, you
All
could
right.
set all that up. Anyway, that's fine.
When did I share this link?
You shared it yesterday, I think.
Oh, is it,
Uh,
is it different from the original one? Oh man.
yeah, it is. Yeah, that's fine. I sent a note to Rose via Slack, so hopefully she can join us. Okay.
Yeah, let's go to her. All
Yes,
right,
how's it going?
good.
Good.
Here's a philosophical question while we're on the topic of philosophy.
Yes, sir.
Why would me and my wife were discussing this earlier. Why would a centuries-old vampire be interested in a high school girl? It doesn't make any sense. Like,
Oh, men will be men even if vampires, I guess.
Hey, Robert, you're just gonna have to wait on that one.
Ask
Just
a
trust
vampire.
on the wisdom of 100-year-old vampire, I guess.
Yeah, when you get old enough, you're like, you know what? Who cares about social norms? I'm a
Oh, yeah.
vampire.
Okay. That's fine. I'll pull out. I'll just get rid of that one. Okay, I'll just delete a message from the other Slack. So anyway, I pinged Rose. Very interesting topic, Pam. When did you read the book, by the way? A long time ago or quite recently?
Yeah, it was like 4 or 5 years ago, long time ago. When I was doing my PhD, like it was, yeah, maybe even longer than that. Yeah.
Hey, what book?
Boltzmann's Atom.
Oh,
It's about the kind of the people history of what we're talking about today, basically.
Yeah, it's a mix of like a biography of Boltzmann plus the science and all that of atoms. There's a lot of stuff I guess I hadn't appreciated. Like, I mean, you read it in a school book, everything makes sense. You say, of course, everybody agreed on this, but people argued over this for like a long time. And Boltzmann killed himself because nobody paid attention to his ideas. Like, he committed suicide.
Yeah. So it's a bit of a sad story, really. But fascinating work. So Rob Neal, sorry, when did you encounter all this ergodicity and equilibrium and all that stuff in economics? Was that just kind of expected and kind of obvious, and not really talked about, or was there any discussion of the background of where it comes from, or is this?
Kind of somewhere in between. I started taking econometrics courses in grad school, and the professor I had was big on this stuff. Lars Hansen, recent Nobel Prize winner, actually.
Okay, wow. Hi, Rose.
So, I mean, that sort of introduced us to the concepts of what made models work and what made time series models work. It's the notion of stationarity and ergodicity. So, I mean, that's sort of been kicking around for a long time. And actually, reading the post for today, I'm sort of reminded of some of my thought processes way back then. Trying to think about functions, estimation functions, and trying to characterize how they would converge and what they might converge to. So yeah, it brought back a lot of memories.
Did you, Robert, did you do theory of ergodicity and stuff like that? Did you do StatMech in your machine learning stuff? Or?
that was a stats PhD. We had to do a required course on random processes, and so.
So this is familiar to you all then.
Right. So for me, like, ergodicity, yeah. Yeah, basically, but it was taught entirely from a probabilistic standpoint. There was no connection to, even when we learned things like Brownian motion, like we would never connect it to physics or finance or anything like that. It was just pure theory. The closest that we had to application was kind of queuing process stuff, which, I guess, queuing processes is like, suppose you got people, you have some people walking into a restaurant, and then they have to get in line to get their food, and there's 3 lines open, and the average line has the waiting time has a certain probability distribution, and for an individual. And so, like, what's the, then you ask a whole bunch of questions about that system, like how long, what's the what's the marginal improvement in waiting time for adding a new register for something like that. So these are kinds of questions you ask in operations research, like, what's the right way to board an airplane?
Right. Did you touch on this in physics, Pam, in your PhD?
Yeah, I mean, I did a bunch of stat MEC courses. Although, I mean, they do mention ergodicity, but it's sort of taken for granted when they're sort of deriving these macroscopic like rules in thermodynamics. You just average, and nobody questions that whether or not taking that average is appropriate. I guess it was nice reading about it here. I always took it for granted. I never thought that might be problematic in some cases. And I mean, another direction that, like, we had these courses on like probability that covered Markov chains and random walks. And I think that's coming at it from a mathematical perspective. But yeah, all of this was like 15 years ago at this point. So I don't claim to remember everything I did.
Right.
Course on, I ended up taking a course on, like, on Coursera on dynamic systems. Another one on kind of chaos theory stuff, and that touches on this a little bit.
Yeah, I still have Strogat's dynamical systems book on my shelf, still trying to read it. It's 1,000-page, but it's really fun when I start reading it, but there's always something more important to be done than reading about dynamical systems, unfortunately.
Which book is that? Sorry.
It's called, what's it called? I think it's called Nonlinear Dynamical Systems and Chaos, something along, like, if you just search Steven Strogat's on Amazon, that's his main book.
Oh, there it is. Okay, great. Thank you. All right. I read all the books you recommend.
Well, this one is going to take you a while.
Okay. Yeah, no, I'm really enjoying, actually, I just finished, I'm kind of going back to the start of Kuhn's book, which was extraordinary as well. So that's something else we should try and get to. Rose, do you have any prior exposure to this stuff? I guess ergodicity and statistical mechanics, is that in your history at all? I think you're muted.
I'm on mute and my
Yeah, you might need to kill your video.
Really bad this morning. No. Yeah, let me do that.
Yeah, that's better.
No, I don't have a lot of history with this. Purely just reading on my own, and of course with the Santa Fe Complexity Institute. At one time, I've done a couple of the dynamical system classes there.
Yeah, I mean, this is a little off topic, but I mean, I see ergodicity as sort of being one of the fundamental issues about machine learning that's kind of gotten swept under the rug.
Yes.
That sounds pretty on topic. I think that's the angle we're looking for eventually.
So, I mean, does anyone want to have a crack at defining ergodicity from your appropriate discipline? It just means this is the Poincaré thing where any given system near equilibrium will visit all possible states given enough time, right? That's
Well,
the
there was a
idea.
little bit more than that, right? I mean, up until that point, I thought I understood it, but it has an extra requirement that it should have equal chances of visiting all the states uniformly. Like I didn't appreciate that requirement because I would say most systems don't satisfy that, right?
Yeah,
Yes.
kind of in the machine learning framework, it's kind of ensuring that your training data set is really representative of the problem you're trying to solve.
Right. And your training data has to be ergodic, right? So you can't have a bunch of people from one particular, like you have to have a uniform sample distribution, right? If you sample everything from this bit, then you're missing all the others. And
Yeah, I mean, you know, it wouldn't be appropriate to exclude Canadians or something.
So how do we map this to a like a supervised learning problem? Because ergodicity is a time process, right? Like how do you think of it in terms of training data?
What if? So when I first learned ergodicity, it was like some. In my notes, I actually forgot. I learned of it as a. Yeah, I was thinking of Markov processes, and so you just had kind of like nodes for states, and you're transitioning through states, and then you can kind of analyze the graph to see if like, okay, this is in the long term, there's like every state's going to be visited and will be like revisited, and so that was just like a property of a graph. And then like I remember reading like Nassim Taleb's books or his blog posts, and he's going on about ergodicity. I'm like, what's he talking about? And then this is a graph thing, right? And then I think kind of learning what it meant in finance, and Robert, correct me if I'm wrong, but it meant that like in a time series that so let's say the time series, I think if I remember it correctly, and then you had multiple time series, so like maybe corresponding to multiple individuals, for example, and that's averaging within one time series was the same as averaging across all the time series. I believe that's what it was, and so like, is that right?
Under certain parameterizations, yeah, I think that'd be correct.
And it's important because, saying, for example, that, my financial planner says, invest your money in, a broad index fund, and it's, it's going to go up whatever, and they kind of show me historic averages. So I guess that's across all time series, but like for any given individual, there might be, you might be one of those people whose 401k gets wiped out right when you need it. Well, on average, that doesn't happen, right? But even as I say it out loud, I feel like I'm missing something because that point seems obvious.
Well, I mean, there's another interpretation of ergodicity, and it's sort of an intuitive one. It's kind of sampling. So make sure you're sampling from the universe and not a subset of it.
Right.
Which is kind of impossible, right?
Exactly. That's where I was going. Yes.
And so there's the whole thing about the infinity space, right? And so the only way we can do this is to put some sort of boundary around it. And that then ends up participating, right?
Yeah. This gets back to finite games, basically, where you can't play the infinite game because you can't be ergodic, right? So you can't make any predictions. So, yeah.
Yeah, well, that's kind of silly.
What's that? Sorry.
Well, I mean, look, we got to make decisions. We have data, and sort of, at least from my thinking, the notion of ergodicity is one of specifying the parameters of the problem precisely enough that we don't have to worry about Rose's problems.
So this is the universal construction where whatever the best theory that we've got is, however terrible it might be, that's the one that we should use, right?
Yeah, pretty much.
I think where that gets interesting is when you come into defining what the macro states and the micro states are. Because the definition of the macro state and the micro state then ends up playing into the dynamics of the system.
So I think you need to have knowledge of the microstates in order to build the statistical model and to even have a chance of claiming ergodicity. So you need to have some kind of a microscopic model, but you don't necessarily need a macroscopic model. And I think that's the key point here, is that if we can specify an individual microcomponent or agent fairly rigorously, then any behavior that emerges out of their interaction over time is statistical in nature, but it is also, we can draw useful inference from that, right? So in the past, when I've given this medicine to people with this disease, they've gotten better. Therefore, I should prescribe that medicine to people who appear to have that disease now.
But I thought maybe I misunderstood what you said. I think at the end of the day, if you go, so your microstates would be, let's say, every person that gets this medicine, but then the macrostates, you're still trying to infer an average for the entire population. So that is your macrostates, kind of like the temperature in the statistical mechanics. You can follow all the atoms around bouncing each other. Eventually, you will have to come up with a macrostate you care about, such as the temperature. Otherwise, it's just one big table of numbers and velocities, and it's useless. Like, you will need to decide what you want to get in aggregate out of this, which is your statistic. And I think that's what Rose is saying could backfire if you choose that one wrong, or you go for the wrong one, or you don't discover the right one.
Yeah, I think I found I found the example of ergodicity from Taleb, and I think it kind of has intuitions from machine learning. Can I?
Of course.
Yeah. So, right, we're talking. So the key insight I think he's trying to bring is that the probability of an outcome for a collection of individuals doesn't apply to, or doesn't necessarily transfer to one individual. So if, for example, you were going to try and observe some outcome and some strategy and its outcome amongst an ensemble, amongst a population, it doesn't necessarily mean that you should bring that, that's a strategy that you should employ. And so the example given is, all right, so say we have a casino, we have 100 people go, they each bring $1,000. They play a game that has on average a 50% return. So that means that's 50% of 1,000 is $500. This, however, that game that they play also has a risk that on average, 1 out of 100 people will go bust. So they'll lose all their money and wind up with nothing, and they can't keep playing. So in this case, suppose that the 28th gambler goes bust. It's not going to affect gambler 29's play. Now, so on average, then each player makes about 500% per day, and 1% of gamblers go bust. So kind of using standard cost benefit analysis, you have a 99% chance of gains and an expected average return of 50%. If you do make a gain. On now scenario 2, you got one person going and they play this same game 100 times in a row. And they start with $1,000 and they employ the same strategy. So first day he's making 50%, he gets $500. Second day he gets $500, and so he keeps making money. And then, but on day 30 or something like that, he loses and goes busts, and now he loses all of his money. And so and so the key insight here is that while on average, everybody would have like you had a high chance of making money on one play and not going bust. If you by averaging over averaging over people, if you average over time, the outcome changes. This actually reminds me of a time when in Boston the lottery ticket, because every time there's a lottery and nobody wins, it just goes into the next pot. And so what happened is that the expected value of a ticket became positive because the pot was so high. But you were still going to, that doesn't mean you should go take your life savings and spend it on tickets because you still had a very low chance of losing. You were going to, if you had infinite pockets, then you could keep playing until you won. But chances are you were going to run out of money before you won. It was the same kind of idea here. So like, I think that kind of, I feel like, I mean, it definitely has a feeling and sense of like, I'll just, in causal inference, for example, like the results of a randomized experiment might not really apply to you if, the treatment is something, if you would have had a better alternative treatments to, that doesn't feel as connected if I say it out loud.
Yeah, I thought
it's training data.
Yeah, I thought that when you started, before you gave the two scenarios, I didn't agree with what you said. I mean, the scenarios are clear. It makes sense in time. If you keep doing the same thing, it's not the same situation as 100 people going to the casino or 1,000 people going to the casino. But I mean, but that's different than saying if you have some kind of a statistics that on average works as an individual, it's not necessarily the best strategy. Those are two different statements. Like if we know, for example, vaccines are whatever helping 80% of the people, you should just take it. You shouldn't be thinking about maybe sure. I'm not one of those people.
Yeah. I mean, I think it's more like the definition of ergodicity, if I remember, based on this example, is that the probability calculated across the ensemble is equal to the probability calculated across time. And a non-ergodic process violates that, which is to say, like, playing Russian roulette and you make money if you win. If obviously the consequences of playing as an individual are different than the average winnings. But I guess for machine learning, I'm not really sure how it feels like something to do with training data, but I mean, it makes sense in finance, right? Because it means like all the advice based on average returns on an investment strategy, maybe you should be a bit more risk averse because while the market can stand to get wiped out and just come back and average it over 50 years, you can't. People are like, the stock market has done great over the last century. I'm like, I'm not going to last that long, and I really need one bad outcome to kind of have, if you were retiring right after the 2007 financial crisis, it would have been bad. I don't know. I have trouble kind of figuring out what this means for machine learning, though. I guess it means.
So let's start then with something very close to our hearts. So time symmetric causality, is there such a thing? How can that be? The whole point of causality is that A happens before B. Therefore, causality is time asymmetric, right? So we can't have symmetric time if causality is real.
I think from a statistical mechanics perspective, like all dynamical laws of physics are time reversible. There is no causality. We need causality because we lose some information when we aggregate and there is entropy changes. Yes, if you are in the time scale and length scale of little particles bouncing around, I think either way in time is equivalent.
Right. So I agree with you, right? And I have a physics background as well. So I would argue that time is symmetric, but how can that be if causality is real? That doesn't make sense to me.
Well, in our time scale, it's not symmetric, right? Obviously.
Right, and then we go down the Boltzmann's rabbit hole of are we just in a local bit of time and find a local bit of the universe where time seems to be flowing in this direction, but we could travel in the spaceship somewhere else and would appear to flow the other direction.
Yeah, I never really understood these arguments. Like it goes above my head, but I mean, if you look at the equations, it makes sense. But like if you try to wrap your mind around it, I mean, we are so used to time going in one direction that I can't imagine it the other way.
What is there's that term arrow of causality? Is you familiar with it?
No.
I know arrow of time. Is that
Arrow
a
of
different
time.
thing?
Arrow of time. Yes.
Yeah, that's later in the article. If you want to read on, they talk about this extensively. That's very messy.
Yeah, I
So-
mean, here's something I've sort of been puzzled about this. So, if I drop my cell phone on, from a high enough distance, on a hard surface, it's going to break. Okay, now if I tried to, and so the causal part is I drop it, then it breaks. But if we look at that backwards in time, it breaks, then I drop it. But why, I mean, sort of logically, it's kind of sort of a one-to-one mapping, isn't it? And if so, then does it matter? I mean, I can certainly think of processes that are sort of one-to-one and ones that are kind of many-to-one.
But statistics offers a prediction, right? It's not a hard prediction. It's not saying this will be the case in 1 second from now. It's just softening that to this is likely to be the case 1 second from now. And if you run the experiment many times, then if you average the results, having run the experiments many times, then it will tend to asymptotically approach some equilibrium, right? So, I mean, we're talking in our separate conversation, Rob, we're talking about equilibrium all the time, and we're trying to create multi-agent systems that move towards equilibrium. What does that mean? Does that just mean that there's some, so this to me is expressed by the diminishing the step size in your machine learning thing, right? So at first you have a very large step size so you don't get stuck in a local minima. But then once you've found a minima that you like, you then decrease your step size, and you keep decreasing your step size until you find a stable point. But if the system was ergodic, couldn't I just keep randomly sampling with just randomly sample the entire distribution and just pick the best one? I mean, why do we need to form this image of a manifold that's kind of reaching some minima if I just roll the dice 100 times and take the best value?
Well, I think the problem is the dimension of your parameter space is so humongous that you will never find anything useful if you randomly roll the dice.
Fair enough. I mean,
so
this
that,
yeah.
There is a interesting, in another meetup I'm attending, we had an interesting discussion. So there's a couple of papers going around, one by Yann LeCun, who's like a creator of convolutional neural nets, arguing that neural networks are actually extrapolating, they're not interpolating. He looks into these dimensionalities and does a bunch of experiments and comes up with a controversial argument that we're not interpolating between training data, we're actually extrapolating, and it's generalizing, and we don't know why. But then Francois Chollet, who works at Google, is another big deep learning guy. He has a Twitter thread, and he argues the exact opposite. Of course, we are interpolating, and he makes arguments. And we had a live discussion of which point of view you believe in, because the conventional wisdom is that most of the things we care about lie on some low dimensional manifold in the data. And that's why we don't need 1 billion data samples. Maybe we just have 1 million is good enough to get a really good idea of what the data distribution is. And you don't need to have infinite samples. But Yann LeCun tries to argue that the dimensionality is so large that that even with 1 billion samples, you still haven't sampled the space enough. And the fact that if we get some good results out of these systems is we don't know why. So that's still going on, a Twitter war or Reddit war. If you want to get into it, I'll share some links. It's kind of interesting to see. I'll be curious what you guys think. I'm on the Cholet side because the other side seems a bit mystical. Like if you just say these neural networks are extrapolating and somehow they're getting the answer right, that's like the equivalent of saying, you fit a 10th order polynomial into 2 points and you're extrapolating and you're right. You get the right results. That doesn't make any sense to me.
So what was Charlotte? So wait, Yann LeCun was, sorry, can you break down the arguments again?
So Yann LeCun was saying it's all extrapolation. It's impossible to interpolate in a large dimensional space of neural networks because every step you take is going to be extrapolation because the space is so big. And he makes a lot of mathematical and statistical argument and experiments. But yeah, he uses some controversial definitions of interpolation and extrapolation that I don't think I think that's where it goes wrong, but I'm not qualified to.
What did Francois Chalet say?
So he's saying the conventional thing that everybody thinks at the moment that Yann LeCun is saying is a misconception that so the manifold dimension is actually pretty small. And if you interpolate, if you're on the manifold of, let's say, all the natural images, and you can interpolate between any two data points and get new points that are valid. And that's interpolation. And if you somehow miss about part of the training or part of the data, then you won't be able to interpolate because you haven't sort of sampled enough from that part of the distribution. So what he says is what everybody thinks, the way like we have enough data and we have a lower enough dimension of manifold that you can interpolate. So if you have the results of two things, you can sort of estimate the result of the third one you haven't seen because you're fairly sure that that third thing is somewhere between the first two. So yeah, his argument is pretty.
Saying, how could it be interpolation if like the dimensionality is so big that you'd essentially, I mean, he's arguing because the dimensionality is big, then it's a kind of extrapolation.
Yeah, so that's what Yann LeCun is arguing, right? And so I guess, but nobody knows what's the dimension of these manifolds. Like he's just like talking about it, but nobody can actually verify. Like if you're doing MNIST, what is the dimension of the manifold where all the MNIST digits lie on? It's probably something super low dimensional, but I don't know what it is.
Yeah, I'll be interested in reading that if you can send the links.
Yeah, I'll share.
Cool. So is this interesting? Like, is this worth digging into, or is this kind of like, yeah, so what?
I'm enjoying this. I'm glad that you pointed me to this. I would like to keep reading.
Cool. All right. Excellent. So I've been reading some more Kant, and he talks about causality as well. And he makes a claim that causality is time directional quite strongly. And this is really what I'm curious about, is what is the nature of causation, or what is the definition of causation? That is causation time symmetric, like, or not? I don't know. So in order for causality to work, do we need a time asymmetric system? Has this question been answered to anyone's knowledge? Or?
I thought the answer was yes, but I defer to Robert. I hope it was, otherwise I completely missed your course, the point of your course.
Repeat the question.
So in a time symmetric universe, time can flow either way, and the laws of the system still hold, right? But in a law of cause and effect, the effect can never occur before the cause. And so it is causality itself that is, or systems that are causal in nature that actually are driving the arrow of time in one direction, because causal systems can't run backwards, right? You can't have the effect before the cause.
So, I mean, that sounds right to me. I would say that, put it this way, whenever I've hit the whenever people start talking about arrow of time or quantum mechanics in the context of causality, I just stop reading.
You just tune out. Okay.
That's so, okay. Not because it's not important. It's just because it feels like I have more immediate fish to fry before I dive into the area of the literature. But I know it's a thing. Let's see here.
Okay, so it's not kind of one of the preconditions of studying causality. It's just kind of one of these under the rug monsters that we don't bother to muck around with. Okay.
I mean, no, people are thinking about it. I just haven't. I'm trying to let's see, where's that book? Where's that? So that book by Bernard Sokol. Because I know they do a lot of stuff.
Real Causality, is that the one?
I can't remember what it's called. Let me Janzing and
While Robert's digging that up, let me pose
elements of causal. Sorry, let me find something and then go ahead. Let me dig this up. Go ahead.
Here's kind of the way I think about it, perhaps a little bit different, and that is, if we ran the process backwards, is there information we could get from it that we couldn't get going forward?
What is information? And I'm not trying to be a dick. Just what do you mean by information?
Okay, yeah, I mean, I started to think about this about a year ago, and it seems that, I don't know, paradoxically, it might be sort of a way of confirming causality. So you run the process forward and you have your standard causal interpretation, X causes Y. But if you run it backwards and it doesn't work, then sort of the forward causal interpretation makes sense.
So, and I'm just throwing this out there just to try and provoke thinking. Are explanations time reversible? Right, so McGilchrist makes the suggestion that explanations are caused by a system one kind of decision, and then we try and justify that decision a posteriori, after the fact that we've made the decision, so that we try and fabricate these explanations after we've come to a decision. And if we can't fabricate explanations, then it's not a very good decision, right? So that's what McGilchrist is suggesting, which is a very causal process. If he's wrong, which he could be, then it might go the other way, where our explanation actually ends up going the other way, and actually
there is a I guess an important concept. I don't know how it comes into explainability and what McGilchrist thinks, but from a physics perspective, there's also reversibility versus irreversibility, right? If you dissipate something, if it's the irreversible process, by definition you're losing information, just with the entropic definition of information, and you cannot go back. You have lost information. There is no way to go back. So I would assume that that also means that you cannot. There is probably multiple explanations that might describe equally well the backward direction, whereas there's only one explanation that explains one way. So that's one way to think about it.
Well, that's sort of a verification of a forward causality, right?
Yeah, but I mean, if you have, I guess, bowling balls that, let's say, they conserve energy and you don't lose any energy, I mean, it's equally, you could say right ball hit the left ball or the left ball hit the right ball, right? It's equivalent. So, but I guess I think most relevant examples in real life is everything is irreversible, right? Something breaking is somewhat irreversible. When it gets tricky is that there's always a finite probability that your device collects into the sort of the original version, right? It's not impossible, but it's just very, very unlikely. I think that's when it gets a little bit tricky. that we've never seen this sort of thing because it's so unlikely, but technically it's not ruled out by the laws of physics. So I think people argue, are we missing a law of physics, or it's just the way it is and it's all probabilistic and maybe it's allowed for things to go collect into these complex structures. We just don't see it because it's not likely. And I don't think I know the answer to that, or anybody knows the answer to that.
So just orbiting back to causality very briefly, then perhaps causality or a causal event actually destroys information so that the consequent state space that the system can move into is reduced by the causal event occurring, right? So the cause actually essentially is negating the possibility of a whole bunch of futures. And since we can never visit those futures based on the cause, we don't have to be time symmetric because we can't get there to be time symmetric from, as it were.
Huh. Makes sense. But I mean, certainly in economics, there are a lot of processes that we would think of as sort of causality going both ways.
Sure.
Supply and demand, or price and quantity.
But I don't think you're destroying information in that situation, right? You're not precluding possible futures. I don't know. I just find this.
So the price will affect the demand will affect the price.
Right. So you can have circular causality then, which is fine. I mean, it exists, so I'm not saying it's wrong. So the price reduces the state space of the demand, but there is still a state space, and then the demand can respond within the possibilities of that state space. And so when a choice is made, then that collapses the probability distribution of the possible steps, the next steps. And so we can keep narrowing the field, as it were, to move towards equilibrium. Perhaps that's a good way of thinking about equilibrium.
I think
These causal events essentially negate the possibility of certain futures. Once again, I'm just struggling with the idea of causality and time symmetry. They don't.
I have something I'm going to send. 1 second.
Well, David, while Robert is saying, another book recommendation for you. I really enjoyed this. If you're interested about information, so it's a thin book, so this one is not as bad as the Strogatz. It's called Why Information Grows by Cesar Hidalgo. I've actually read one of the chapters like multiple times, like the best explanation of like entropy and structure and all that I've ever read in any book. It's not a technical book, it's a common book, but it's really, really well done.
Okay, thank you. Keep it coming. I'll read them all.
I'm curious, like I don't know if like the second half of the book goes into like information in the cities and things of that sort. I wasn't particularly interested, but you might be interested, but the first half of the book was really good.
Cool. All right, thank you. That's great. Robert, any insight?
Yeah, here.
You want to share the screen or whatever you want to do?
Yeah, I want to put so stick it in the
Chat? Sure.
chat. 1 second.
Ooh, that's the book.
Can't copy. Why is it too long?
Let me just check Audible, see if there's an Audible version. Yes, it's on Audible. Got it.
What was the name of the book? Sorry.
Why Information Grows by Cesar Hidalgo.
Yeah, I posted a link to that. It's a PDF.
It's only
It's
3
2
pages in
pages,
that.
Pardon?
It's just a summary. I think the one you posted is only 3 pages of the book.
Oh, yuck. Let me see what else I can get. Hold on.
No, that's fine. I've got the audiobook, so that'll be my walk for the day is to take a run at that. I might do some more Kant. It's really interesting, actually. I'm reading a little bit further into Kant, and he actually talks about functional programming of all things. I had no idea, but yeah.
Kant talks about functional programming.
But Kant talks about functional programming and why it's better. It's really, really interesting. If you get into the transcendental logic stuff, which is just completely whacked out, it's just such a weird conversation. But he actually talks about functional programming in 1780. Can you imagine? Yeah.
Robert, do you want to explain what you posted? Or is that for our reading pleasure later?
We can read it now if you like. I mean, it answers the question of the connection between
Principle of
arrows.
independent mechanisms can be viewed as the principles of as a principle of physics. Consider the special case where 2 variables. If
Can you just
S
read it
is
out
the-
loud?
Yeah, sorry. I mean, I can read it out loud, or we can just read it separately. That's no idea.
I like you have a lovely voice.
So consider the special case of 2 variables. If S is the initial state of a physical system and M is a map describing the effect of applying the system dynamics for some fixed time, then S and M are independent. Here we can assume that the initial state, by definition, is a state that is not interacted with the dynamics before. So this is Kant's idea of a priori. Here the initial state S and the final state M of S are considered cause and effect. Accordingly, M is the mechanism relating cause to effect. There's the problem. Okay, we'll talk about that. To understand this, consider a beam of n particles propagating in exactly the same direction, are approaching the same object where they are scattered in various directions. The directions of the outgoing
upon hitting the object, right?
Upon hitting the object, yeah. Oh, sorry, yeah, I missed that. Yeah, okay. The directions of the outgoing particles contain information about the object, which, while the beam of the incoming particles does not contain information about it, perception has occurred. The assumption that particles initially propagate exactly in the same direction can certainly be weakened. If there is some disorder in the incoming beam, the outgoing beam can still contain about the information about the object. Indeed, vision and photography are only possible because photons contain information about the objects which they are scattered. We can easily time reverse the scenario by hand designing an incoming beam for which all particles propagate in the same direction after the scattering process. Certainly, such a beam can only be prepared by a machine or subject that is aware of the object's shape and then directs the particles accordingly. As a matter of fact,
potentially creating an optical illusion, for example.
Yeah, exactly. Yeah. As a matter of fact, particles that have never been in contact with the object cannot, a priori, there's Kant, contain information about it. Then the independence of S and M can be maintained if we consider the process directing particles as part of the mechanism and reject the idea of calling the state of the hand design system an initial state. Instead, the initial state then refers to the time instance before the particles have given the fine-tuned momenta. The fact that photographic images show what has happened in the past and not what will happen in the future is amongst the most evident asymmetries between past and future. The preceding discussion shows that this asymmetry can be seen as an implication of the independence of S and M. The principle thus links asymmetries between cause and effect with asymmetries. Okay. So Kant basically makes the claim that causality is exactly like this, which is there is some mechanism that is defined a priori, some function that is defined a priori, and no amount of experience can affect that process. So to bring that back to the conversation we're having right now, statistics is based on experience. It's not a priori, it's a posteriori, right? So statistics is not causal because causality in Kant's definition, at least, has to be a priori. Right? Your function M has to be defined before you experience anything, before you collect any data. This process that you're looking for has to already exist. And so you can't infer causality from experience.
That's what the Judea parallel also says, I guess, right?
Is that what he says?
Well, I mean, I think he says you need to put in causality. You don't get it out of your data.
Although, like a lot of the kind of interesting stuff with causal discovery happening now is using inductive biases beyond conditional independence. And some of those inductive biases are based on intuition from thermodynamics. Say, for example, that going, if I have two things, and I don't know which is a cause and which is effect, I can kind of pick the direction where I see some kind of behavior in terms of entropy, right? Because entropy is asymmetric. But like, for example, like if say for example, it seems to be because of entropy that like the noisiness of the cause will be less than the noisiness of the effect, for example. And so using that as a kind of inductive bias is something that I think is actually a promising area of research.
So are you saying that there's less information in the effect than in the cause? Right? At the time before the cause, there was this much information. Then after the cause, there's less information. Is that what you're saying?
So I guess the idea is like let's
so equilibrium must have a cause.
So the idea would be that like if I were to okay, so like let's say like there's image classification. There's a presence or absence of a cat, and then there's the image, right? Now you're a completely naive person, and your robots kind of coming to this reality for the first time, and reflecting on this one variable, which is 50 by 500 by 400 set of pixels, or and this other variable, which is just the kind of binary presence or absence of an object, and you don't know which direction causality. You know there's a causal relationship there, but you don't know which direction it goes. And so in other words, reasoning about the kind of like going from this simple binary kind of outcome to this complex outcome of pixels and images and colors and noise and distortions and contrast and this and that, that kind of reflects how causality in this universe tends to accumulate entropy as it goes along. But that's something that is outside of Pearl's framework. This is these are new ideas. And so like the way it shows up often in practice is by using kind of additive models with non-Gaussian noise or nonlinear additive models, and kind of using that assumption to kind of say, you're regressing two things, and you don't know which one causes which. And so you look at the residuals for regressing Y against X, and you look at the residuals for regressing X against Y. And based on the structure of those residuals, you say like, well, the residuals with the simplest structure, that's the right direction.
That's interesting.
I didn't follow all of that, sorry. But,
I need to hop. I gotta join my wife for dinner.
okay.
Thanks guys. I enjoyed this. Please
Great.
continue.
So it'll be kind of more of the same next week then. We'll go a little bit deeper, and I'll do some more reading and see if I can pull some more stuff in. But
Sounds good.
so that was Vladimir Shukov. Oh, he's gone already. Never mind.
Yeah,
Right,
I found
guys.
the book. Yeah, thanks.
Oh, did you find it? What was it?
It's just the Elements of Causal Inference by Shukov.
Okay, Elements of Causal Inference. Thank you. That's great.
Yeah, if you just put everything Robert wrote in quotation in Google, you'll get the book.
Awesome. Well, thanks everyone. Rose, you've been very quiet. I hope you got something out of this. And we will see you all next week. All right, take care.
All right,
Take
thanks,
care.
everybody.